Okay, today we're reviewing how to convert linear measures of area, and measures of volume. And we'll do the same calculation, the same conversion factors, but with one vital difference at each step. You'll see that for linear measures, the conversion factors are raised to the power of 1. With area measures, the conversion factors are raised to the power of 2. And with volume measures, they're raised to the power of 3. So I asked you to convert from 1 mile to the same measurement. What is 1 mile in kilometers? And we know that there are a few exact conversion factors that we would use to do this conversion. First of all, we have to know that there's exactly 5,280 feet per mile, exactly 12 inches per foot, exactly 2.54 centimeters per inch. This is by definition. And there's exactly 100 centimeters in a meter, and there's exactly 1,000 meters per kilometer. So there are no significant figures in this conversion factor because they're all exact numbers. So we don't have to worry about significant figures. The number we get is the exact value. So when we multiply all these numbers together, we get 1.609344 kilometers. And if we want to convert it into meters, we move the decimal place over 3 times because we're multiplying by 1,000. There's 1,000 meters per kilometer, one with 3 zeros, so that's how you know you move the decimal place 3 points over. And we get that 1 mile is equal to 1,609.344 meters. If you wanted to convert it into millimeters, you would move the decimal place over by 6 places because there are 1,000,000 millimeters in a kilometer. And the way I got that was that there's 1,000 meters in a kilometer, and there's 1,000 millimeters in a meter. So 1,000 times 1,000 gives you 1,000,000. So there are exactly 1,609,344 millimeters in 1 mile. Now what if I wanted to convert a square mile, meaning if I had a square that was 1 mile long and 1 mile wide, that would be 1 mile squared. If I wanted to convert that into kilometers squared, I would use all the same conversion factors, except now each one of the conversion factors is raised to the power of 2, because it has to be applied over 2 dimensions. So 5,280 squared, remember this squared power is distributed to each one of these things, to the mile, to the 1, to the 5,280, and to the feet, and so on all the way down the line. So this becomes 144 inches squared per foot squared, and whatever 2.54 gives you squared, and so on. So we get at the end 2.589 kilometers squared. Now, here's the tricky part. If I wanted to convert kilometers squared to meters squared, I have to recall that in a square, which is 1 kilometer by 1 kilometer, it would be 1,000 by 1,000, which means it's 1,000,000 meters squared. And that's why when I convert from kilometers squared to meters squared, I don't move the decimal place by 3 points, but by 6 places. I move my decimal place over 6 places because there's 1,000,000 to 1 conversion factor. So 2.58 kilometers squared is actually equal to 2,589,000 meters squared. And the same thing applies now if I want to convert from miles cubed to kilometers cubed. All the same conversion factors as with the linear conversion, except I raise each one to the power of 3. The result is 4.168 kilometers cubed. And if I wanted to convert this into meters cubed, I bring to mind the fact that in a cube that is 1 kilometer high, it's 1 kilometer high, 1 kilometer wide, and 1 kilometer long. That would also be 1,000 meters by 1,000 meters by 1,000 meters, which is 10 to the 9. So the conversion factor from 1 kilometer cubed to meters cubed is 1 billion. And that's why I would move this decimal place over 9 places to give the value in meters cubed. And if I wanted to go to millimeters cubed, I recall there's 1,000,000 millimeters per kilometer, so 1,000,000 times 1,000,000 times 1,000,000 is 1 to the power of 18. So that would move this decimal place over 18 times. It would equal 4.16 times 10 to the 18 millimeters cubed. The next thing I wanted to review is our knowledge of Lewis structures, and one of the ones I asked you was thiocyanate. And we did the normal accounting of how many electrons are in the molecule. We're talking about valence electrons here. Sulfur has 6 valence electrons because it's a chalcogen, it's a group 16. Carbon is in group 14, so it has 4. Nitrogen is in group 15, so it has 5. And then there's one extra electron for the minus charge. So that's a total of 16 electrons, 16 valence electrons in thiocyanate. So I begin by drawing the basic skeleton of the molecule, which is carbon in the middle, sulfur on one side, nitrogen on the other. That uses up 4 electrons for these 2 bonds. And then I have 12 more to use up, so I'm going to put them 6 around sulfur and 6 around nitrogen, and then we'll do an accounting to see what the formal charges, if any, exist, are going to be. Sulfur, let's look at the octets first of all. The octets here are satisfied for sulfur, they're satisfied for nitrogen, but carbon only has 4 electrons that it can call part of its octet shell. So the octet is not satisfied for carbon in this structure, so definitely we have to modify the structure. And there are 2 ways we can go with it. But first, let's account for the charges on the molecule. Sulfur wants to have possession of 6 electrons in its valence shell, but it here has 7. 2, 4, 6 plus the 1 from the bonding pair gives it a formal charge of -1. It wants 6, it has 7, therefore it has an excess of 1. Nitrogen wants to have possession of 5 electrons, but here it's possessing 7. So in this situation, it's going to have a formal charge of -2, and the carbon is going to have a formal charge of +2. Let's try looking at first getting rid of all the formal charges on nitrogen. So if I was to take this lone pair and put it as a bonding pair, we'll take this lone pair and put it as a bonding pair as well, we'll end up with the following structure. It will be triple bonded carbon and nitrogen, and the formal charge here will be gone, but sulfur will still have a -1 charge. So that's one possibility. And also there's still 2, there's a lone pair right there. Or we can go the other way, where instead of having both of these lone pairs go in, we can only have one of them go in on one side, and one of the sulfur's lone pairs can go in, and we'll end up with sulfur double bonded to carbon, and carbon double bonded to nitrogen, and then the formal charge will be on the nitrogen instead of on the sulfur. Both of these, as it turns out, are valid Lewis structures, and as it turns out, the chemistry of thiocyanate is such that sometimes the sulfur atom bonds to some other molecule or atom, and in other times the nitrogen molecule binds to some other molecule or atom. So there's, depending on where the negative charge is when the molecule forms, you'll get different compounds. So thiocyanate has a peculiar two-pronged approach to balancing its charges, but these are equally distributed in the Lewis structure. Both of those species can be found. The next example would be arsenite. Arsenite is composed of an arsenic atom with 3 oxygen atoms and a charge of -3. So when we count for the number of valence electrons, we notice that arsenic is a group 15 element. It's in the nitrogen group, so it has 5 valence electrons. Oxygen is a chalcogen, so it has 6, and there's 3 oxygen atoms, and then of course there's a -3 charge, so we have to add 3 electrons to the final diagram. So there's 26 electrons that have to be accounted for in arsenite. So we put arsenic as a central atom, we'll put the oxygens as satellites, and then we use up 6 electrons, 6 electrons by doing that, just from these bonds. So we have 20 more electrons to disperse. If we go 3 by 6 on the oxygen atoms, that leaves us 2 more electrons. And whenever you have extra electrons, after dispersing them on the satellite atoms, you place them on the central atom. That's what I did here. So arsenic has a lone pair. Now let's account for the octets. Arsenic has a fulfilled octet, 2, 4, 6, 8. All the oxygen atoms have fulfilled octets, 2, 4, 6, 8. See, they all have the same symmetrical structure. So all the octets requirements are fulfilled. Now let's look at the charges. Arsenic wants possession of 5 electrons, and indeed it has 5 electrons. 2, 3, 4, 5. Oxygen wants 6, but each one of these has 7. 2, 4, 6 plus 1 is 7. But you see that this is the arsenite anion, so it's supposed to have a formal charge of -3. And if each oxygen carries a formal charge of 1, it totals to -3. So that would be the Lewis structure of arsenite. With phosphate, when we do the accounting, we find there's 5 electrons from phosphorus, 6 from oxygen, and there's 4 oxygen atoms, and then there's the extra 3 for the -3 charge. So a total of 32 electrons have to be accounted for in the phosphate Lewis structure. We put phosphorus as the central atom, the 4 oxygen atoms as satellites, and then we disperse the remaining 24 electrons on the oxygen atoms. That uses up everything. See, 2, 4, 6, 8. If you subtract 8 from 32, that gives you 24 left over, and 4 times 6 gives you the 24. So all the electrons have been used up. But when we look at we know that all the octets are fulfilled, but when we look at the formal charges, we see that each oxygen ends up having a -1 charge, and the phosphorus ends up having a +1 charge. So that's 5 formal charges within one molecule. If we just move one lone pair so that it forms a double bond with between phosphorus and oxygen, we now have this modification of the Lewis structure where the oxygen atom now has no formal charge, neither does phosphorus, and the other 3 do have a -1 charge. So overall, the molecule will have a -3 charge, and due to resonance, this double bond is shared equally over all 4 positions. So the bond character of the phosphorus and oxygen is 5/4, 1 1/4 bond, essentially, because those electrons are equally shared. In hypophosphite, which has a structure PO2 3-, we do the same accounting. It gives us 20 electrons in the structure. We place the 2 oxygen atoms as satellites, and when we place the remaining electrons, first we begin by putting them on the oxygen atoms, so 2, 4, 6, 8, 10, 12. 12 there, 14, 16. That leaves us 4 more electrons. So the remaining 4 are placed on the central phosphorus atom. And that when we count the formal charges, we'll see that each oxygen atom is going to be -1. Phosphorus, which is a group 5 element, wants to have possession of 5 electrons, but here it has 2, 4, 5, 6, so it has 1 more than it wants, which means it's going to have a formal charge of -1. So